low pressure, and the chemical potential mu1, mu2, up to mu c, the chemical potential of the components. Those are the potentials. Okay, and this is the chemical potential for component 1. Component 1 will go from high potential to low potential. When system is at equilibrium, every phase has the same T, the same P, and the same chemical potentials. Okay, then we have what we call QI. These are the corresponding extensive variables, which are defined by derivative of the derivative of the internal energy with respect to one variable, keeping all the other Q's constant. So here we have entropy minus volume, number of moles of 1, number of moles of 2, the number of moles of C. So for example, ui is equal to du dni, keeping S minus V, and Ni does not equal J constant. And you can look back over to the first chapter and so on and see that that's the case. But basically you see that this is this is the chemical potential of 1, and N1 is the quantity that is transferred down a potential gradient. Okay, so if you have two regions, one has a higher mu1 than the other, then the number of moles of 1 will move from high to low. So this is the quantity that's transferred down that potential gradient. Entropy is basically transferred down a temperature gradient, and minus volume is transferred down a pressure gradient. You have a pressure gradient, volume will move one side. Okay. And these pairs of variables here, pairs of corresponding variables, occur in the equation 9. They come what I call the fundamental equation. du is equal to TdS minus PdV plus mu1 dN1 plus mu2 dN2. Okay, the fundamental equation of thermodynamics, here you have T and S, here you have minus P and V, mu1 and N1. If you write out the Gibbs-Duhem equation, you get the same pairs of variables in each term. Okay, so those are your thermodynamic variables, potentials, and okay, when a system is at equilibrium, I'm reading on page 68, the potential variables are the same for all phases. So when the system's at equilibrium, all phases have the same T, they all have the same P, and they all have the same mu1, mu2, mu3, mu4. That's the criterion for equilibrium. They do not, however, necessarily have the same values of Q. Three phases can be at equilibrium, and they can have different volumes, different entropies, and different number of moles of the phases. So first of all, some phase diagrams you can draw tie lines, and in other phase diagrams you can't draw tie lines. Right? Like I said, if you have an isopleth, you can't draw a tie line because the phases don't have a composition in the plane. If you're plotting one variable versus another, and you're keeping only potential variables constant, then since all phases have the same T, the only variables, a phase diagram has one axis, a y-axis, an x-axis, and a whole bunch of variables that are kept constant. If the only variables that are kept constant are potential variables, they are the same in every phase. Therefore, all the tie lines are going to lie in the diagram. So if you have a diagram where the only things that are constant are temperature, pressure, chemical potential, then everything lies in the diagram. If you keep, however, if you keep a certain number of moles or a volume or something constant, then you have a diagram where the tie lines do not necessarily lie in the plane of the diagram. We'll give you an example in a minute or two. Okay, so if only variables which are held constant are potential variables, then the compositions of all phases will lie in the plane of the phase diagram, and the lever rule may be applied. However, if an x tends, so examples were found in figures 1, 2, and 5. Look at figures 1, 2, and 5. Convince yourself that the only constants are temperature, pressure, and chemical potential, and those diagrams have all tie lines in the diagram, and the lever rule works. However, if an extensive variable, such as composition, is held constant, then this is no longer necessarily true. It might be true, but it's no longer necessarily true. Okay. It could be true because you could be on a quasi-section, like the CaOSiO2 system. Okay, you're going across an isopleth, but it's a quasi-binary. Okay, and you can look at figures 3, 4, and 30 and see that that's the law of adjoining phase regions, 1956, applies to all single-valued phase diagrams, As a phase boundary line is crossed, one and only phase either appears or disappears. Okay, so if we cross the phase diagram line, okay, here's an example, figure 4. As I cross the phase boundary line, one and only phase appears or disappears. So, okay, these are solid solutions. Remember, this is a BCC solid solution of vanadium, chrome, iron, carbon in it, and so on. This is a monocarbide solid solution, and so on. This is an isopleth, so you can't apply the, that is, composition is held constant, so tie lines aren't in the plane. This only tells you what phases are present, doesn't tell you how much or what their compositions are. But it tells you that here, at this point, I have BCC plus MC, and when I cross the line, another phase appears, FCC. Or when I go back the other way, the FCC disappears. One and only one phase appears or disappears as you cross a line in a section. Now, here you have two phases, here you have FCC, here you have FCC plus MC. You can check every region here, every line, every phase boundary. That's the case. One and only one phase appears or disappears as you cross the phase boundary line. Okay, now I maintain that that applies to every phase diagram section that I've shown you so far. And right away, you could look at a binary phase diagram like this, in which you have AB and you have alpha, beta, liquid, and here you have liquid plus beta, and here you have liquid plus alpha plus beta. Sorry, alpha plus beta. And then you could say right away that as I cross this line, the law of adjoining phase regions does not apply, because I'm going liquid plus beta. As I cross the line, the liquid disappears, the alpha appears, so two phases have changed, and so something's wrong. And what's wrong is that I have not crossed a phase boundary, I have crossed a very narrow two-phase region. Okay, now this sounds like I might be splitting hairs, but this is very important for the whole algorithm. Where am I here? Okay, I want to go down to figure 31 then. Shows this. Okay, there we go. This is my binary phase diagram with the eutectic opened up artificially. Okay, what I've done is I've taken this diagram and this infinitely narrow three-phase line. I've artificially shown you that it's really a very narrow three-phase region. In reality, the top line and the bottom line are coincident. But if you look at this as really a top line and a bottom line, which are just happen to be on top of each other, now you can see that the law of adjoining phase regions apply. Liquid, alpha appears, alpha, liquid, beta appears, liquid disappears. So when I cross this line, I said here, it looks like I'm going from here to here, but I'm really going from here. I'm crossing the top line, and then I'm crossing the bottom line, and every time the law of adjoining phase regions applies. Okay. Now, why is this not just fooling around? So if you look at it that way, that there's a top line and a bottom line that are on top of each other, then this diagram has exactly the same geometry as the one I showed you before. Okay. If you look at a pressure temperature diagram now, at a pressure temperature diagram in which I had the three phases, say again solid, liquid, or gas, or alpha, beta, gamma. Once again I cross over here and it looks like the law of adjoining phase regions doesn't apply, but once again this is not a phase boundary, this is a infinitely narrow two-phase region. Okay, and again I can consider this diagram to be opened up like there. So here's your pressure temperature diagram, and I'm showing that this is really a narrow two-phase region. Okay, so really these two lines are coincident, they're on top of each other. And similarly the triple point is really an extremely tiny or infinitely tiny three-phase triangle. Okay, so if you open the diagram up, this is what it looks like. Okay, and now you see that you have, again, you have lines where four lines come together. Okay, and the law of adjoining phase regions applies everywhere. So the triple point is a degenerate three-phase triangle. Alright, so now I'm going to go to figure 33. And I'm going to say that all nodes in a diagram, all nodes in a phase diagram look like this. Now you can see that in any phase diagram section, you have nodes, which are where four lines come, all nodes where phase boundaries meet, and all nodes in a phase diagram section are of this type. The only nodes are nodes that have four lines coming together. And you'll have a number of phases, alpha 1 to alpha n, which are common to all four phase regions around it. And then over here, so at the top node you have, in the top phase region you have just the alpha phases. In all other phase regions, over here you have the same phases plus another one beta. Over here you have the same ones plus gamma. And down here you have the same ones plus beta plus gamma. And that's the only kind of node that you would get. Okay, and you can go back then to that figure, whatever it was, the figure 4, 6, whatever at the beginning. I'm not going to go back to it now, someday I'm going to get this organized now. Let's go back to figure, what the hell was it? The iron chrome carbon thing. Figure 4. Go back to figure 4. If you go back to figure 4, what we looked at a minute ago, you will see that every node on figure 4 looks like that. There are four lines coming together. Well, I better go back to figure 4 because I think it's important. I will go back to figure 4. Okay, so here we have, let's take this node here. Okay, so four lines coming together, 1, 2, 3, 4. Up here, BCC plus MC, those are the phases that are common to all four regions around that node. BCC plus MC alone. Over here, it's BCC plus MC plus another one, FCC. On this side, it's BCC MC plus M7C3. And down here, that's number 6, that's this. BCC plus BCC plus MC plus both of the others. So these are alpha 1 and alpha 2, that's beta, that's gamma, this is alpha 1, this is alpha 2 plus beta plus gamma. And all regions are that way. Okay, it's 2, here you have 2, 3, 3, 4, here you have 1, 2, 2, 3. Okay, all nodes are like that. And if you look at the figure 31 and 32 with the, once I get this thing done, of course, they're all going to be in the same if you look at this, it's the same way. Here you have one phase. Liquid is the common to all four regions. That's alpha 1. There's only one alpha plus liquid, beta plus liquid, alpha plus beta plus liquid. Same thing. And even here it's the same thing. Here you have one phase plus another, one phase plus another one, all three phases. Every node has four lines together. There is a rule called Schreiners rule, which I will not derive for you here, but it is derived somewhere in the book. And Schreiners rule, okay, here you go, whoops. Schreiners rule, which is talked about on page 71, is shown by the dotted lines. Schreiners rule states that you take the region here that has the lowest number of phases, that doesn't have the beta, the gamma, and you consider those two boundaries. Either both those lines must extend into this line must extend into this region, and this line extends over here. Okay, this line must extend here, and this line extends here, or they both extend into this region. That's the only two possibilities thermodynamically. And you see many, many phase diagrams drawn in which Schreiner matrix rule is violated. It's a thermodynamic rule. Either this is correct, or both dotted lines are into this region with beta plus gamma, but you can't have this going here and this going here, for example. I won't prove it, but it can be proven thermodynamically in the general case. Schreinermacher did it in 1920-something for the simple case of a ternary isothermal section. Then Hillert said 20 years ago that it should apply to a general section, but he didn't prove it, and a few years later I proved it. But it is the case, general case.
Just a question.
Yeah.
If you take the two lines on the left side,
Yep.
there is one that will end in the plus gamma, and the other one will end with only the alpha phase. So they will end.
No, this is, you're talking about these two lines?
The two on the left side, the red and the blue one.
Well, that's okay. No, it's the two lines around the region with just the lowest number of phases.
Okay.
The region that does not contain beta or gamma, you consider those two boundaries. One must go into the beta region, the other into the gamma region, or they both must go into the beta plus gamma region. And we talked earlier about this this other extension rule where you have a binary phase diagram, remember? I said this kind of extension is not, you can look at that as if you open up this region, you can see that that's this particular case of, a special case of Schreinermacher's rule. As is this one, even here I said that, when these lines must go like this, that's also a special case of Schreinermacher's rule. All the extension rules are basically based on Schreinermacher's rule. Okay, now we're almost ready then, or I guess we are ready, to say how you can calculate all phase diagrams with one algorithm. You go to the phase diagram program of FactSage, and you might think that when it calculates an isothermal isopleth or a binary phase diagram or all these different diagrams, mu oxygen versus iron nickel ratio, that it had to have some sort of a different algorithm, but it uses exactly the same algorithm, which is based upon the phase rule and these geometrical rules I just showed you, and the law of adjoining phase regions. And this is based on the theory of zero phase fraction lines, which is illustrated best going back to this figure 4 again. Alright, and the zero phase fraction lines, which are mentioned up here, and this is described on page 71. Okay, when we were back in the mid-90s with FactSage, we were trying to write phase diagram program, we thought that this was going to drive us crazy because every kind of phase diagram you had for a 3, 4, 5, 6 component system, depending on what you had for axes, would require a different algorithm, and this would be really hard to do. But now we have one algorithm, so every diagram I've shown you here has been calculated with FactSage using exactly one algorithm. All the diagrams with enthalpy, volume, chemical potential, whatever, there's only one algorithm. And the algorithm is based on the concept of zero phase fraction lines. The concept was introduced by Gupta, Morale, and Novotny in 1986. I mentioned it here. And a couple of us actually read this paper at the same time, and we said, that's how you do it. Okay, so on this diagram I show zero phase fraction lines by different colors. Each zero phase fraction line applies to a particular phase. So the red line is the zero phase fraction line for this solution, the black one is for the BCC solution, and so on. A zero phase fraction line is a phase boundary where the particular phase is just there, but at zero amount, where it's just about to appear or just about to disappear. Okay, so the BC, let's take the black line. The black line here for the BCC phase. You see that it exists on one side of the line, but not on the other. The law of adjoining phase regions, this is the phase that disappears or appears across that line. So the phase is just, on this side it's there, on the other side it's not there. So as you come up here, you have no BCC. When you reach this point, the BCC begins to appear with a zero amount, and then it gets more and more as you cross the line. So it's the zero phase fraction line. Okay, so the red line is a zero phase fraction line for M23C6. It's on this side and it's not on this side. And you can see that these are continuous lines. The zero phase fraction line for BCC goes like that. The zero phase fraction line for M23C6 goes like that, and so on. If you draw a zero phase fraction line for every phase, you've drawn the entire phase diagram. Okay, now a zero phase fraction line can be calculated by fact stage by simply iteration. I'll show you what you do. First of all, what you do is you set up your axes and constants of the diagram, and then you go around the axis, you go around the frame, you go around the outside of the diagram, and you look for the ends of the zero phase fraction lines. This is easy to do using the target option of fact stage. Basically, it's done automatically for you. The target option you find when a phase just appears. So, what you do, formation target. So you're going along here, and you have BCC plus MC. You do a little, you go every 10 or something. You go here, 2 phases, up 3 phases. So somewhere between here and here, the BCC appeared. So now I just iterate back and forth, and I find the point where the BCC appeared. So by targeting, I can find the end of the zero phase fraction line. I just make this up until I see something change, and then I go back and forth. Okay. And so I find the end of every zero phase fraction line as I go around the diagram. Then I take every zero phase fraction line and I move along it from one end to the other. So I've identified this end of the BCC phase fraction line, and I found this end over here as I went along here. So I start here, and now I move along a little bit, and then I move up and down until I get the amount of BCC to be just 0. That gives me another point, then I move along another little bit, and I change the angle back and forth. And I just follow this line from one end to the other, keeping the amount of BCC just equal to 0. So this is just a line following. I move along, and I just keep doing a huge number of formation targets going back and forth. Now I don't have the nodes come out automatically. I don't have to know anything. The program doesn't have to know anything about geometry. It doesn't have to know that 4 lines are going to come together at a point. That'll happen automatically. The zero phase fraction line will go like this, and then it'll come along here, and the zero phase fraction line will be calculated. And after I've calculated every zero phase fraction line, 4 lines will come together at that node. Okay. It doesn't have to know anything about the geometry. It just has to follow the zero phase fraction line for every phase, keeping the amount of that phase equal to 0, but just on the verge of appearing. And then the entire diagram then will fall out. Now there's a couple of things. It is possible that a zero phase fraction line does not cross the boundary of the diagram. A zero phase fraction line can begin and end within the diagram. But then you will probably come across that while you're following in the second step. As I move along a zero phase fraction line, I suddenly find that I have a new phase that I never noticed before. Well, I remember that point and come back to that later and follow that zero phase fraction line. Okay, the only problem with this algorithm where it can fail is if you have a zero phase fraction line that does not intersect the boundary of the diagram and also does not intersect any other zero phase fraction line. So I can imagine I have a ternary phase diagram here. This is an isothermal section in which I have one phase here, and here I have 2 phases, like a liquid miscibility gap that's completely an island within the one phase region. In that case, these are zero phase fraction lines, but I wouldn't find, as I went around the boundary of the diagram, I would not find it. Okay, so the only way to do that then would be to change the boundary of the diagram to here or something, but these island gaps are very rare.
Is it possible that at the node that the angle is so big that you can, when you are come at one point, that you just don't continue and take the other ones?
Well, no,
I don't have.
The program will take care of that. I mean, it'll keep looking. It'll go all around until it finds where to go. The line must continue. It can't end. Well, it can end at I'm simplifying, but you can have a miscibility gap like this. I mean, this zero phase fraction line's going up here, and this one's coming up here. Gooder's program takes account of the fact that kind of. If we call this L1 and we call this L2, then this is a zero phase fraction line for L2, and this is the one for L1. But when they meet at that point, he realizes it's a critical point. This is taken into account. Other phase that might appear in the middle is, I say you have a phase like, you have a phase diagram that has something like this. Here you have this is a sigma phase, which is only within the sigma phase boundary doesn't cross the axis of these zero phase fraction lines don't cross the axis of the diagram, but you're going to find them when you're following the other lines. Okay. Now to show that, okay, so that's fine for this isopleth, but now you can see that this works for all these other diagrams. So let's go to these. Okay, so there we go. So this is your binary phase diagram. And remember now, the binary phase diagram, you have three phases, alpha, beta, and liquid, and these are your zero phase fraction lines. So the alpha phase appears along this line. The alpha phase is on one side but not the other. Goes down here. This is your beta phase, zero phase fraction line, and this is your liquid, zero phase fraction line. Now you see that the liquid, this line, that the eutectic then is calculated twice. Because, as I said, the cap is really not okay, when you look at it this way, now you see what's happening. The zero phase fraction line for the beta phase comes along here, comes along here, and along here. The zero phase fraction line, the liquid phase, goes along here. They simply happen to be on top of each other. Okay, but you see now exactly the same algorithm can be used. Okay, this diagram is calculated with exactly the same algorithm as for the four-component system I just showed you. You go along the edge of the diagram first to find the ends of the zero phase fraction lines, and then every zero phase fraction line is simply followed from one end to the other, and the diagram falls out automatically. Exactly the same algorithm. You don't have to know anything about nodes or... Okay, so the program doesn't have to know any thermodynamics. It just sets up the axes, finds the ends, and follows the lines from one end to the other. And similarly, on a diagram like the pressure temperature diagram, where you have alpha, beta, and gamma. I mean, the zero phase fraction line, this is the zero phase fraction line for alpha, that's the zero phase fraction line for beta. Every line is calculated 2 times, that's it. Calculate one side and the other side. Okay, so all the diagrams I showed you, whether you're dealing with volume, whatever, it's all the same algorithm with the zero phase fraction lines. And that has made the whole thing very simple, and so now you can have a general algorithm to calculate the phase diagram, and that's talked about in section 7.4. Okay so far? Okay, I'm going to go on a little bit longer because I missed last week, so. All right, so far that then explains how you can calculate any phase diagram section using one algorithm, and I'm hopefully showing you how this whole thing follows from the, so go back, you have the phase rule, which is based upon the thermodynamic notions. Then you have the concept of the rules. There's the law of adjoining phase regions and so on, the zero phase fraction line concept, and that then leads to the single algorithm, and how basically all single valued phase diagram sections obey exactly the same geometrical rules. There's only one unit of construction. The only unit of construction is the nodes with the 4 lines coming together, as I showed you with the alpha plus 1. Okay, and Schreinemaker's rule is the only extension rule that applies. All the other diagrams are basically limiting cases or special cases of the same thing. Now it also depends very much, again, of course, on whether your axes are going to be potentials, temperature, pressure, chemical potential, or extensive variables or ratios of extensive variables. But this doesn't affect the zero phase fraction line concept. That's the same no matter what you got. Now, however, can you plot anything versus anything, keeping anything constant, and get a single valued phase diagram? And the answer is no. Unfortunately, you can't just plot anything you want. And here's an example of where you can't plot anything you want. This is water, H2O, pressure volume diagram for water. Right. So this is the phase schematic, but that's what it looks like. And at this point here, for example, you have two phase regions which overlap. There are two solutions. Here you could have a liquid in equilibrium with a gas, or you could have a solid in equilibrium with a liquid, because they're different temperatures. Okay, this is not, although I'm at one point of the diagram here, this point in this two-phase region, or I could have a pressure and a P and a V, but at different temperatures. The same P and the same V. The temperature is different, so I'm in different regions. Now obviously this diagram is not what you want. It's not single valued. There's not, every point of the diagram does not represent a unique equilibrium state of the system. Also, it doesn't follow the zero phase fraction line concept. So now it doesn't mean it might not be useful, but it's not a single valued phase diagram. You can't do that. Here's another example. This is the copper-nickel-sulfur system. Copper-nickel-sulfur system at 427 degrees Celsius. Okay, remember we did that diagram, the iron-nickel-oxygen diagram. I plotted log PO2 versus the iron-nickel ratio. Back figure 5, I think it was, and that all worked out quite nicely. Now this looks very similar. There I had iron-nickel-oxygen. Here I have copper-nickel-sulfur. There I plotted oxygen pressure. Now I'm plotting sulfur pressure. So what's wrong? There I plotted oxygen pressure versus the iron-nickel ratio, and everything was cool. Here I'm plotting sulfur pressure versus this composition, the amount of nickel, and it's not cool because I have over here I have two two-phase regions which are intersecting somewhere here. This could be in the this could be in an FCC plus nickel sulfide region, or it could be in the FCC plus copper sulfide region. There's something that's kind of screwed up here. This region up here doesn't exist. You can't realize that region. If you take this diagram though, and rather, the difference was, what is the difference then? What's wrong? On the iron-nickel diagram, remember this was nickel over iron plus nickel. I did not say plus oxygen. I just took the metal ratio. Here I'm throwing in the total mole fraction. Okay, take this and simply knock sulfur off down here. Now, this is equivalent now to what I had before. This is log PS2 versus the ratio of nickel over copper plus nickel in every phase. And now the diagram is quite nice. Okay. If you try to calculate this diagram with FactSage, it won't let you do it. If you go to the variables window, a phase diagram, and you try to set up these variables, it won't let you pick them. It'll let you choose those variables, but it won't let you choose those variables. It also won't let you choose pressure and volume. Okay. You can plot a PT diagram or a VT or whatever, but you can't plot a PV diagram. It won't let you do it, and it won't let you plot this diagram. This axis down here has to be copper, but it'll let you calculate this diagram because that worked, this one because that's correct. It won't let you calculate the other one. Okay, so the question might be then, what are the rules that apply to calculating a diagram that's going to be single valued everywhere? Because this is really essential, so that you know that the diagram you're getting is going to be interpretable and also calculable with a phase diagram program. This doesn't mean necessarily that rules. A pressure volume diagram for water, if you're in that region of pressure and volume, is not going to be single valued. If, however, you say you were limiting your calculations down here or up here, then it would be okay. And for a different system, the reason this happens is because water is particularly strange in that the solid is less dense than the liquid. Ice floats on water, but most materials the solid sinks to the bottom. And in that case, this diagram, these 2 points here are flipped around. And so in such systems, PV diagram was going to look like this, which is okay. But you can't be assured that it's going to be, and there could be other triple points that work the other way around when you have 3 different phases there. Okay, so you're not assured. It's this. This isn't necessary, but I'm looking for the sufficient conditions for a phase diagram to be single valued, not the necessary conditions. And the rules are given on page 73. So we're talking about these conjugate pairs of variables, where I said you have the chemical potentials and you have the corresponding extensive variable. Each potential has a corresponding variable, which is the extensive quantity that's transported down a potential gradient for the corresponding potential. And the Qi is du dq as dud. Sorry, phi I is du dqi. Sorry. Okay, from each corresponding pair, you choose one and only one. So I'm going to choose, what I'm choosing is I'm going to choose the variables, which are the axes and the constants of the diagram. And from each pair, I choose one and only one. I can choose t, but then I can't choose s. I can choose v, but not p. I can choose n, but not mu. I choose one from each pair, no matter which, but I choose one from each pair. Section 2 is the, so once again you can see, well, the PV diagram didn't work because I had P and V. I'm choosing them from the same pair. I've violated the rule. Second rule is define the size of the system as some function of the selected extensive variables. The extensive variables are these ones. I have to define the size of the system. Okay, so I could say that the total number of moles is equal to 1 or something, which is what you usually do in a binary diagram. You say n1 plus n2 is constant. But I don't have to. I could say I have a diagram at a constant number of moles of iron if I want. Or I could choose a constant volume diagram, and so on. And then the other extensive variables have to be normalized. So the simplest example is, I have n1 and n, a binary system with n1 and n2. Okay, so I know these are not two separate variables. What I do is I will say let n1 plus n2 equals constant, and then I normalize the variables as x1 is n1 over n1 plus n2. I vary. x2 is n2, but then it's not independent. Okay, so I'm going to get one less variable because something has to be normalized with respect to the total size of the system. And then I take the variables, the potential variables, and the normalized extensive variables, and I choose two of them as the axes, and I keep the others constant. And that's what the rules say. And here's your example. So here you have, okay, in order to do this, I'm going to have to go flipping back and forth, but figure 1. Figure 1 is the iron molybdenum binary phase diagram. So we go to the iron molybdenum binary phase diagram. Oh, for Christ's sake, look what I did. I screwed this up. That's page 73. Okay. The iron molybdenum binary phase diagram, it's a two-component system. So your variables are Tp, mu iron, and mu molybdenum. Okay, I've chosen the ones that are underlined are the ones I've chosen. I've chosen one from each pair, so I've chosen temperature, pressure, number of moles of iron, and number of moles of molybdenum. I've set my size of the system by defining the total number of moles. And my variables then are temperature, pressure, and my normalized number of moles. So temperature, pressure, and composition are my variables. Okay, so what I do is I keep one of those normal variables constant, and I plot the other two. Okay, so I keep pressure constant, and I plot temperature versus the mole fraction of molybdenum, and I get a proper diagram. All right, let's go to figure 6. These are the examples. Figure 6. All right, once again now, I have iron, chrome, sulfur, and oxygen. Okay, so this is page 74. Back to page 74. All right. There we go. So iron, chrome, sulfur, and oxygen, so my 4 components. So I have 4 components, so I have the temperature, pressure, and the 4 chemical potentials. And the ones that are underlined are the ones I've chosen, one and only one from each pair. I'm going to set the size to be iron plus copper. Okay, my variables then will be temperature, pressure, and I've chosen the chemical potential of oxygen, chemical potential of sulfur, and a normalized variable, which is the number of moles of, do you believe, How many mistakes? I corrected that over and over and over. This should be mu of chrome, of course. And this should be the number of moles of chrome. How do I do that? This should be chrome. It's the chrome system. So it's chrome over iron plus chrome.
So the course is useful.
All right?
The course is useful.
Course is very useful. Oh, I went over this so many times. Okay. This should be mu of chrome, and this should be n of chrome because it's the iron chrome sulfur oxide system. Okay, so those are my variables. Temperature, pressure, chemical potential of oxygen, chemical potential of sulfur, and my normalized extensive variable. Okay, and if you look then back to the diagram on figure 6, that's what I plotted. Chemical potential of sulfur versus chemical potential of oxygen, keeping the temperature constant and the molar ratio of chrome over iron plus chrome to be 1.5. All right. Go to figure 3A. This was this isopleth that I've talked about several times. Okay, you're plotting temperature versus the molar ratio of aluminum to magnesium plus aluminum. And that's then here with the temperature, pressure. You have the three mole numbers constant. I'm choosing my size as magnesium plus aluminum. And my phase diagram variables are temperature, pressure, normalized aluminum over magnesium plus aluminum, normalized zinc over magnesium plus aluminum. And you can see what I've kept that one constant and plotted that versus T keeping that constant. You can check over the aluminum, silica, oxygen. This was the one component phase diagram in figure 7b with this the PT diagram. So I plotted T minus V and the number of moles of aluminum. Okay, the size is the number of moles of aluminum silicate. The size is given by simply fixing the number of moles of aluminum silicate. The phase diagram variables are then of the temperature and the molar volume. The volume divided by the thing that I'm defining the size of the system. That's in figure 7b. Okay, where I plotted temperature versus molar volume. Now we see what's gone wrong with the copper-nickel-sulfur system. Remember in figure 37 and 8 I plotted the copper-nickel-sulfur system in two ways. In one way I had the two phase regions overlapping. In the other way the two phase regions didn't overlap. You see the problem. Here I've chosen copper, temperature, pressure versus number of moles of copper, number of moles of nickel, and the chemical potential of sulfur. And defining the size of the system as the total number of metal moles, I plotted temperature, pressure, chemical potential of sulfur, and the number of moles of nickel over copper plus nickel, and that gives me figure 37, which is correct. Okay, so figure 37. Is the correct one. And I plotted temperature was constant, plotted chemical potential of sulfur versus the ratio of nickel over copper plus nickel, according to the scheme that I just showed back here. Okay, well I'm choosing the variables like this, and so everything's correct. What was wrong with figure 36? In figure 36, as you recall in figure 36, everything was the same except I put the number of moles of sulfur down here in the denominator of the mole fraction. And now you see the problem is that I'm using the number of moles of sulfur in this variable and the chemical potential of sulfur here. And this is not permitted because I can only choose one. I've used, in the variables, I've used the mu of sulfur, but I've also used n of sulfur somewhere in a variable. That's not permitted. I can't use it. Once I've chosen mu of sulfur, the number of moles of sulfur can't appear in any variable anywhere, or else I can get into trouble. Okay, as long as I follow those rules though, everything's fine. And then I encourage you to read the rest of that section there. I don't think I have to go through every single thing. Okay, I just want to say one last thing and then we'll stop. Corresponding phase diagrams. Okay, so those are the rules and phase diagram program of, as I said, the phase diagram program of backstage is set up that doesn't let you do that. You can only choose axis variables that obey those rules. Okay, and that way you always get a single valued phase diagram and the law of adjoint and the zero phase fraction line procedure works, the algorithm works, and you can calculate all the diagrams. And you know that any point of the diagram is going to be a single value, so you can't get into trouble. Now there has been problems. I said this is sufficient conditions. A PV diagram for a substance other than water or in certain regions is okay, but you can't calculate it with FactSage. Now, we have had many discussions, well maybe somebody would like to calculate it. Well, you can't calculate it with FactSage. You can calculate it with equilib program and save it up, do a whole lot of slices and then plot the thing up yourself using the figure program. But you can't just go right to the phase diagram program and do it. This is really the only place where you're going to see the whole thing done this way. This is, I think, summarizes the whole theory of single component, of single valued two-dimensional phase diagram sections. This describes the entire geometry of it is described in terms of the zero phase fraction lines, the law of adjoining phase. The things I just went through is the whole theory of single valued phase diagram sections. You might want to look at corresponding diagrams. You see that, say you have a diagram that you might replace the axis of one diagram by its normalized conjugate variable, then you can have what we call corresponding diagrams. So what we did is, if you go to figure 7, and I think this is important, if you go to figure 7, you have corresponding diagrams. Here we have pressure, temperature, and here I've replaced, this diagram corresponds to this one. Here I've replaced the pressure by its corresponding normalized variable. So in the group PV, the one in the lower diagram, the y-axis is pressure, and the upper diagram is the molar volume. This is the corresponding variable. And you can see how the diagrams correspond. Every two-phase region, two-phase line becomes a two-phase region. Every triple point becomes a three-phase invariant. And the diagrams correspond exactly. So the two diagrams together give you complementary information. Another example. Was in figure 38. Oh, I got it right on. Figure 38 is the iron-oxygen system. Okay, here you have your iron-oxygen system. And this is the temperature composition diagram. Mole fraction of diagrams with cut here. But this is your normal temperature composition diagram, going from mole fractions over here. You got iron and two-phase regions, eutectics, peritectics. It's a temperature composition phase diagram. And here I've replaced the mole fraction of oxygen, basically the number of moles of oxygen, by its chemical potential, RT log PO2. Okay, so this is the mole fraction of oxygen here. Here it's the same phase diagram. Okay, but now when two phases are in equilibrium, they of course don't have the same mole fraction of oxygen. Here you have iron, which has virtually no oxygen, in equilibrium with wustite, which contains oxygen. Here you have wustite, which is mainly FeO, in equilibrium with Fe3O4 and so on. When two phases are in equilibrium, however, they have the same chemical potential. Same chemical potential. Okay. So what happens here, every two-phase region becomes a two-phase line. So here you have your wustite plus magnetite two-phase region with your tie lines. Here you have a wustite plus magnetite two-phase line, giving you the chemical potential of oxygen when those two phases are in equilibrium. Okay, so every two-phase region here you have your liquid plus magnetite two-phase region. Here you have your liquid plus magnetite two-phase region is here. So it goes through a maximum of your three-phase invariance. Here you have a peritectic liquid plus wustite plus magnetite with the three different compositions. Here you have your three-phase triple point, giving the chemical potential of oxygen when those three phases are at equilibrium. Okay, so every two-phase region here becomes a two-phase line. Every three-phase invariant becomes a three-phase triple point. This diagram obeys the geometry of a binary temperature composition diagram. This diagram looks like a PT diagram. It's got the three-phase triple points, a two-phase line. And these are corresponding phase diagrams. And they contain complementary information, and when you put them side by side, you got more information than you would over here. You can pick any temperature here. You can say from this diagram you can find the equilibrium oxygen pressure for equilibrium, and on this diagram you can see the two phases that are in equilibrium. Why do the diagrams open up this way? I go through the theory in section 7.7. I'm not going to do that for you, but basically what it amounts to is the can't remember the name of the principle right now. But as you increase the chemical, if you take a system and you increase the number of moles of oxygen and add oxygen to the system, the chemical potential of oxygen always goes up. Okay. So what this means is I go across this diagram this way, I necessarily go across this diagram the same way. If I move from left to right here, I necessarily move from left to right here. Okay. If I go across here and I add oxygen to the system, I necessarily increase the chemical potential. Otherwise, you disobey the, I'll go through it, what the hell you call it. Okay, that's just the, okay, and the same thing would happen with the diagram I showed you, the Al2SiO5, the pressure volume. As I increase the pressure, I must decrease the volume. So as you increase the pressure, you increase minus V. As you increase the pressure on something, its volume always goes down. As you increase the temperature, you always increase the entropy. Don't go the other way. That then is why you can draw these corresponding phase diagrams. Okay, because they always open up the same way. As I go from across here, I go from wustite to magnetite, and it's going to be the same thing here. As I cross the region, I'll go from wustite to magnetite, not vice versa. Okay, so you have all these corresponding phase diagrams, which I think is a useful concept. Let's look at figure 40. Here we have some corresponding phase diagrams for iron, chrome, oxygen. Alright, so this is your iron, chrome, oxygen system at a constant temperature. Here is this log PO2 molar metal ratio diagram, just like the figure 5, the iron, nickel, oxygen. Constant temperature, I'm plotting equilibrium oxygen pressure versus the chrome over iron plus chrome ratio. So you get one of these diagrams like the one I showed you before with that looks like a binary diagram. Over here, I've replaced the number of moles of chromium by the chemical potential of chrome. So you can see that every two-phase region here has become a triple point here and so on, which is fine. But this is more important, is here I've now replaced here this axis is the same, this is the iron-chrome ratio, but now here I've replaced the oxygen potential by the number of moles of oxygen over iron plus chrome. So now as I move up this way, I'm increasing the number of moles of oxygen in every phase. So now my three-phase triple points over here become three-phase invariants over here. They become three-phase triangles over here. Two-phase lines become two-phase regions here, which become two-phase regions here. If I take this now as the ternary phase diagram section, isothermal section of the iron-chrome oxygen system, plotted in what is known as Janicki coordinates. So what I plotted here, this is chrome over iron plus chrome, and this is oxygen over iron plus chrome. That's what this diagram is. So this corresponds to this diagram. Here I've replaced the chemical potential of oxygen by the number of moles of oxygen. So the diagram here, this diagram here has been opened up this way, and now here it's been opened up the other way as well. Every line here gets opened up horizontally, and over here it gets opened up vertically. The triple point here gets opened up horizontally to become a line. Here it gets opened up vertically to become a triangle. But I can now take this diagram, this Janicki coordinate diagram, and fold it up. This is oxygen, so I just fold it up and put the oxygen coordinate infinity, and I end up with your standard ternary triangle. So this is just a coordinate mapping. You're remapping the coordinates. Here I've taken the iron-chrome ratio here and I've just folded up the top to put the oxygen up. This is just a coordinate remapping of that system. So you see that this is basically a corresponding diagram to this. This is your isothermal section. Your classical isothermal section of the iron-chrome oxygen diagram, where you have one phase, two phase, three phase regions. They're corresponding diagrams. So these diagrams then complementary and give you a whole bunch of information. Okay, so that really took 3 hours, but I mean, we missed last week, so maybe we don't have to make this up if we do this one more time. Okay, so please read the rest of. Well, we finished 7.6. Read 7.6.1, 7.6.1. Section 7.7 and 7.7.1 are the whole theory. If you really, I'm not going to go through those. Even next Thursday, I'm not going to go through section 7.7. You're not responsible for it, but I want to do it right once and for all. To really, everything I've told you was not been presented without rigorous proof. Figure 7.7 is the rigorous proof of everything I said. Shows that, defines basically the law of adjoining phase, reads the whole work. So if you really like thermodynamic theory, please read section 7.7 and tell me if you see any problems with it. I do think that it is complete theory of this stuff, which hasn't been presented this way before. Section 7.8, please read it. I will definitely go over section 7.8 though on Thursday, because this is a bit more, well, read the rest of section 7 after 7, 8, 9, 10, 11, whatever, because these are important, especially the oxide phase diagrams, which are probably the worst interpreted phase diagrams, people not understanding how you interpret oxide phase diagrams. So I'm going to go, and you guys are doing that, so I will be going through how you interpret oxide phase diagrams with the PO2s and what it means, a diagram in equilibrium with iron, and PO2 is 1 atmosphere, in the light of the rules that I've just been through here. Looking at it this way, I think it kind of systematizes the whole thing. So please read the remainder of section 7. But if you want to skip section 7.7, that's up to you. And there's the rigorous proof of Schreiner's rule there too, if you want to go through that. Hillard still doesn't think I've done it rigorously, but I think I have. I'm convinced I have. Okay, so yeah. Thank you for your attention. I'll give it up. And, oh, sorry.